This week on Foresight Radio, part 2 of my podcast on quantum computing. In this episode, we'll dive deeper into the realm of the quantum by looking at some of its more esoteric aspects, such as entanglement, the spooky property of quantum mechanics that even Einstein had difficulty in accepting. I'm your host, Tom Koulopoulos, and Foresight Radio is brought to you by our good friends at Wasabi Technologies, the leader in the next generation of cloud-based data storage. You can learn more about them at wasabi.com. And now, part 2 of my podcast on quantum computing. In our last episode on quantum computing, we talked with Bob Sutor at IBM. Bob gave us a bit of a background on what quantum computing is from his perspective. To get a better sense of quantum computing from the eyes of a scientist, I talked to Aditya Jain. Aditya is a PhD student at the Institute of Quantum Computing in Waterloo, Ontario. He's originally from Calcutta, India. Aditya has been inspired by the technology of quantum computing, and he describes it in pretty straightforward terms, although, as you'll come to understand, it is anything but straightforward. Here's a bit of background on Aditya.
I think for me, it all started in undergrad. So my undergrad, I was fortunate to land into a program which combines sort of computer science and natural sciences. The thing that got me into quantum per se it's like a neat combination of my favorite areas. Yeah. Kind of neatly mixes computer science, physics, and math, all three areas.
So one of the things about quantum computing that I'm sure you get asked repeatedly by all of your friends, all of your family, is what is it? How do you make it simple and describe it to people who don't have the background in engineering or in science and computers that you do? How do you simplify it to its essence?
Let me just explain a very, very basic concept of computing that's called a bit. A bit is nothing but two possibilities, a 0 or a 1. That's a classical bit. We say a classical bit. And a classical bit is allowed to exist in only one of these possibilities. For example, let's say I give you the information that a ball is either red or blue. And once you see the ball, it's red, and it's going to stay red throughout. Right. That's a classical bit. Things change when you come into the quantum domain. You can be in a mix of these two possibilities at the same time. And these states do evolve. When you measure them, when you do some operations on them, these states can change. So the color of ball is no longer a property of the ball. Like it changes. And so that's the fundamental difference, I would say.
How long did it take you, when you first started studying this, how long did it take you to get to the point where you said, you know what, now I understand it, I'm fluent in it? If you think about the analogy being a language, if you learn a new language, for a period of time you struggle, you have to translate in your head, you have to think about what you're saying, and one day you wake up and suddenly you think in that language. How long did it take you to get to that point? Or are you at that point?
I think there's this famous quote that nobody understands quantum mechanics. So
it seems that way sometimes,
the reason
right?
behind this quote is like, so for a lot of the classical physics era, everything just followed with intuition. Right. And then at some point you have to accept that intuition breaks down, and you have to accept the experimental results and work accordingly, form your theory accordingly, and because classical mechanics was breaking down at some small level. Yeah. And you need to come up with new laws that go well with the experiments. So that's one of the challenging points of quantum mechanics. Your intuition doesn't quite behave the same way, your regular intuition. But I would say once you spend like a year and a half with the field, you go see in the labs. I'm a theorist, but if you see things happening in the lab, you kind of get more adjusted to it. So I would say about a year of study into the field should get you somewhat convinced.
There are many different aspects of quantum mechanics that we find interesting and befuddling. One of the ones that I think is most amazing is this theory of entanglement. And I believe, and I'm not a physicist or a theorist, so you can correct me if I'm wrong, but I believe Einstein once said something about God not playing dice with the universe. He had a fundamental difficulty with things like entanglement and how those might work, and the fact that they exceed the speed of light was something that he had a difficulty with. What do you think Einstein would say today if he could see what we've done, what you're doing with quantum computing?
So first of all, I want to clear this misconception.
Please.
We don't really exceed the speed of light. We don't communicate beyond the speed of light.
Okay, so this is where things get really weird. This notion of entanglement is one that you come across over and over again if you talk to anyone about quantum computing. In its simplest sense, entanglement is what happens when two objects that are at the quantum level, tied together, behave in a way that is identical between those two objects. Now, the problem Einstein had with that is that if these objects are separated, let's say, by the distance of the universe, then how could they instantaneously have the same state? Now, keep in mind here that when we say the same state, these objects are entangled, but we don't know what state they're in. They know, but it hasn't yet been revealed to us. So once we reveal the state of one quantum object, suddenly the other one has that identical state. And the misconception that Aditya is pointing out here is that we believe that's because somehow communication has exceeded the speed of light. But they're not communicating, at least not in the classical sense. Here's how Aditya describes quantum entanglement.
So this is the no signaling principle, or no communication beyond this, like faster than light principle. It still holds true. Even with entanglement, you cannot communicate faster than light.
Okay.
So that is intact. We aren't breaking that down.
Good. We're safe there.
We're safe there.
Okay.
And coming to Einstein, yes, so there was this paper by John S. Bell, which was one of my favorite papers.
Yes.
So there's a bit of history to it. So Bell wasn't as famous as Einstein, so people weren't really believing him. And then he came out with this really simple paper. Like, simple I say in the sense it's easy to understand and very interpretable. Is no rocket science there. But it kind of disproves what Einstein was putting forward. And coming to Einstein's belief, so there are, if I'm allowed, there are two notions here. One is reality, one is non-locality. So reality basically means, as I was commenting, the property of the object it's a property of the object. So if I associate a color to a ball, it's a property of the object. No matter what, it's a property of the object. That's reality. Coming to non-locality, it's like if two people are far apart, they're called non-local. So it's been proven in literature that a theory cannot be both local and realistic, meaning you cannot have like reality associated to objects and have locality at the same time. So quantum mechanics, it has been shown via innumerable experiments that quantum mechanics violates this one inequality. So there are various inequalities, but there's this famous Bell inequality, which if you have a local and a realistic theory, should have some bound, let's say should have a number upper bound 2. By upper bound, I mean the maximum value of some expression should be 2. But if you use quantum mechanical resources, if you use entanglement, you can go up till 2 root 2. And we are able to do that. We have been shown via multiple experiments.
So you're probably still scratching your head, as am I, trying to figure out what this notion of entanglement really means. The difficulty with quantum computing, which is pervasive in just about every aspect of it, is that we really don't understand at its fundamental, at its core, how it works. So when Aditya talks about reality and non-locality, it sounds a little difficult and obtuse to follow, doesn't it? Think of it this way. There are aspects of science which we constantly have to disprove in order to prove new theories, new frameworks. We go back to the 1500s when Ptolemy's view of the geocentric solar system gave way to the Copernican view of the sun instead as the center of our solar system. You can liken that to what we're going through today as we think about how physics works in the way that we understand it in the real world, what Aditya calls reality, and in this non-localized world of quantum mechanics and entanglement. Here's another approach to understanding Einstein's point of view. This is Lynn Alpert, who is the co-director of the Center for Integrated Quantum Materials at Harvard University.
I think people don't give Einstein enough credit because he was one of the founders of the quantum revolution. It was, that group of scientists in the 1920s and early 30s who really inaugurated the first quantum revolution. Einstein had some serious doubts about quantum behavior like entanglement, which made sense in the context of, trying to find real reasons, real cause and effect. And that's the goal of scientists everywhere. And it seemed unreasonable to him that one object could be entangled with another object across space, and that connection was possible even beyond the speed of light, so that no contact could have occurred between those two objects. And he kept feeling that the science wasn't done, that there must be something that we haven't yet discovered. But ever since then, we've been able to do more and more sophisticated experiments to show that quantum entanglement is real, and it isn't explained by the science we had previously, but also that we can begin to harness those qualities. It is opening a very exciting world for scientists and engineers to play in, and we just don't know what will come out at the other end.
What Carol refers to as the other end is something that we hear a great deal about. It's this question of when will quantum computing be real? When will we start to use it in place of classical computers or in combination with classical computers? Here's Aditya's point of view on the timeline.
The next decade is the most exciting decade of the field, I would say. I think this is a very interesting decade for the field. And if you want to really compare it, you know the transistors existed in 1950s and 1960s. Right. They were of your room size.
Yeah.
We are somewhat at that stage. You have these computers. They are in very special environments. But at the same time, the understanding so far is, okay, quantum computing won't help you in everything. Your day-to-day computing does remain same.
Right.
But we are still in the process of exploring. But there are a large set of problems which it will give a huge speed up.
Wasabi Hot Cloud Storage is a proud sponsor of Foresight Radio and their mission to help rethink the future of how we work, live, and play. At Wasabi, we're helping you take control of a future where your ability to affordably store and leverage data will determine success or failure. Our low-cost, high-speed, fully secure cloud storage blows away Amazon, Google, or Microsoft. And there are no hidden fees for egress or API requests. See for yourself with a free trial at wasabi.com.
When you stop to think about it, if we were to go back to the dawn of the transistor and try to foresee all the ways in which it would change our lives, change our world, it was impossible back then. It is just as difficult today to look forward and answer that same question for quantum computing. Where will it be used? What kinds of problems will it solve? But there are some insights here and some directions. Here's what Carol Lynn from Harvard, who we talked to earlier, had to say about that.
Back in 1947, where Bardeen, Bratton, and Shockley invented the transistor, no one quite knew what to do with it back then. We couldn't really imagine laptops or smartphones or the worldwide internet in the early 50s. And right now, we probably can't imagine the full impact that the quantum revolution might have.
Here's Calvin Leung, who is a graduate student at MIT and an intern at SpaceX. Calvin was also one of the finalists who I interviewed at the Nano Days with a Quantum Leap competition at the Boston Museum of Science.
I think the most exciting thing for me personally is the possibility of simulating really complicated quantum systems. There are processes out there. The Haber process is one of them, where you make fertilizer from ammonia. And this is energetically, it costs a lot of energy input in order to make fertilizer. And if you're going to do industrial farming on a global scale, you need a lot of fertilizer. Right. And so if you can somehow simulate the quantum mechanics of the reaction that turn ammonia into fertilizer, and you can figure out some catalyst, some material that speeds up that process, makes it less energetically expensive, that would be enormous. That would be a huge benefit. And so quantum simulation of molecules and essentially just doing chemistry, right. That's an extremely difficult process to do like end to end. The way people do it now, there are like certain approximations that you can take. When you make approximations, you don't really capture the full picture. And I think one place where quantum computers can really have an outstanding, where they can really shine is using a quantum system to truly simulate another quantum system. That's the only way to do it.
That's a fascinating way to look at it. So we're modeling with quantum computing, we're modeling the natural world in a way that we couldn't with traditional computers, with binary computers, because it would just take too long. But we can model the natural world with a quantum computer.
A lot of times people frame this discussion with quantum computers in terms of power and how quantum mechanics gives you parallelism. But in this case, it's not even that. I mean, there are certain tasks for which quantum computers are worse at than classical ones.
Right.
But for this particular one, simulating a quantum system, the only way to do that is with another quantum system. And this is something that Richard Feynman observed back in the 80s that really launched this whole field of what if in the future we could string together some atoms in a lattice and make them into like a computer of sorts where you can simulate some other quantum system. I think that's fascinating.
Calvin mentioned Richard Feynman. You won't get too far in any conversation about quantum computing without his name coming up. Feynman was one of the most influential physicists of the last century. He worked on everything from the atomic bomb to the Rogers Commission, which investigated the Space Shuttle Challenger disaster in the 1980s. Along with all of his work in theoretical physics, Feynman was, in fact, the father of quantum computing as we know it today. He wrote a paper in 1981 that was called Simulating Physics with Computers, and in that paper he talked about exactly what we've been discussing in these two podcasts, that quantum computers do a marvelous job of simulating the real world, the biological world, the chemical world, which classical computers simply cannot do. And if they can, it would take them millions or billions of years to come close to the kinds of equations that a quantum computer can take on. You often hear about folks like Heisenberg, Bohr, and Schrödinger when you hear about quantum mechanics. They were certainly the ones that laid the foundation along with Einstein for much of the theory. But it was Feynman who ultimately made the connection between quantum mechanics and quantum computing. If all this talk about entanglement and quantum mechanics and physicists is throwing you for a bit of a loop, don't worry. Calvin has a great way of putting this into a framework that makes it understandable.
One analogy I really like is when electricity was invented, people didn't really have a sense for what this was good for or have any intuition for what electricity did or how it functioned. But now everyone knows if you don't plug something into the wall, it's not going to work. And if the connection's bad, it's not going to work.
Calvin makes a great point because, look, at the end of the day, most of us don't really know what voltage is or what watts or amps are. We understand the numbers and that you plug a 120-volt appliance into a 120-volt outlet. But do we really get what's going on behind the scenes, how the electrons are being transferred through the wires? Of course not. And the same thing applies to quantum computing. We may not understand it, but it can still be extraordinarily valuable in how we go about our day-to-day. The last thing worth talking about when it comes to quantum computing and quantum mechanics in general is the level of understanding and education that supports this new field. I recall when I was first beginning to gain some interest in digital computing, there were no courses in school that taught you about computers. I learned on the job, if you will, by quite literally using a soldering iron and transistors. It's tough to do that with quantum because it is steeped in such tremendous science that requires a whole new level of adeptness, instrumentation, and resources. So I asked Carol Lynn, who we spoke with earlier, to talk a bit about her work as Director of Strategic Projects at the Boston Museum of Science, and a bit about the role that she sees museums and education playing in building this new quantum workforce.
As you might suspect, there is not very much teaching of quantum science and physics in K through 12. In fact, it's only within the last couple of years that universities have begun to establish programs in quantum science and engineering. You know, they've been buried inside other departments like physics, applied physics, engineering, material science. And now it's being recognized as, you know, a field. It's a very cross-disciplinary field. And that means that people need training in many related disciplines. And one of the things that science museums are very good at is free-form experimentation with, you know, how do you communicate a difficult concept? What modalities, what visualizations can you use? And that is important experimental work to happen before curriculum is built around these areas.
So there you have it. Quantum computers are going to change the world, or are they? The practical answer is that we just don't know yet. In my last book, Revealing the Invisible, I talked about how John Vincent Atanasoff had designed the first digital computer on which the electronic numerical integrator and computer, also known as the ENIAC, was built in the 1950s. At that time, the only real purpose of the ENIAC was to figure out the trajectory of ballistic missiles. Not much of a use case, and not one which you could expand easily into all the applications that we use computers today. Look, the reality is that quantum computing is going to evolve and clearly is going to change a lot of the way that we think about computing. Will it replace classical computers? From what I hear and everyone that I've talked to, likely not, at least not in the near term. However, it will open up the door to an entirely new way of thinking about computing and how it helps us to model and simulate the natural world. That in and of itself might be a pretty incredible starting point. Where it goes from there, your guess is as good as mine. However, one thing is clear. Stepping into the future is going to require letting go of the past, and at some point, embracing this crazy, spooky new world of quantum computing. To find out more about quantum computing, just check out the links on the Foresight Radio homepage at foresightradio.com. Thanks again to our sponsors for this episode of Foresight Radio, Wasabi. Take a look at how Wasabi is changing the rules of the game for cloud storage at wasabi.com. And thank you for listening. If you enjoyed this podcast, please be sure to subscribe to Foresight Radio and to share it with your friends and your colleagues. This is Tom Koulopoulos. I look forward to joining you again soon for another episode of Foresight Radio, where we explore the future of how we will live, work, and play in the 21st century.